Let's get started. This is your Canvas page. I just wanted to point out that in week 10, I haven't put this week's information yet, but in week 10, we did a problem, I think on Wednesday, where we were talking about a maximizing and minimizing something, and it took a really long time to discuss it. We're trying to find the critical points in the inside, and then we tried to find critical points on the boundary. And in finding the critical points on the boundary, we let some things equal to, we took a look at a function or something like that, and then we let x equal to something as a function of y, or y is equal to some function of x, and then we condensed our problem into a two-dimensional problem by examining the boundary. But in examining the boundary, it's like a constraint. And so what I did was, because that particular problem was kind of long-winded and complicated, and I think we got through it in the class. I remember there was one problem there where it looked like I got the wrong result, and then we corrected ourselves and we moved on. But anyways, because this particular problem was kind of long and complicated, decided to type up the solutions and include some pictures. And as soon as this thing starts, we can talk about it. So this is the problem, and I'm not going to go through this in detail, so I'm just going to walk through it real quick because it's online available for you to download and take a look at. But this is our problem, and then we found one critical point at 0, 0, and then we decided that we didn't have to use a second derivative test because we're not looking for local max and mins, we're looking for absolute max and mins over some closed bounded region. So we got one critical point, and then we had a z value of 0 for that. And then so we took a look at the boundary. So this is where it got kind of difficult. And what we did was we took a look at the boundary, which is a circle, x squared plus y squared is equal to 1. And then we solved for one of those variables and put it into the function. And as we put it into the function, we tried to see the critical points around there. And then we found, I think we found 2, but there was actually 3, so I ended up putting 3. And then I found x values for those points, and then the corresponding y values by putting it back into this highlighted equation. And then I put those values into the f function to get the z value. So you see these points are on the boundary, and these handwritten numbers here are the z values of those things. But we also needed to talk about the endpoints as well, and so I also included that there's a possible, because this thing is supposed to happen, this function is supposed to happen for x values that are between -1 and +1, including -1 and +1. So in this kind of calculus analysis, I didn't include the positive and -1, so that was to be treated differently. And with positive and -1, that's how we found those -2 and +2 values. So here's a summary for that. We have one critical point. We have the other points that are on the boundary, and then we have the boundary of the two-dimensional region. And then we have the actual boundary here. And then it looks like the highest and lowest points are positive and -2. Okay? And here's a viewpoint from the top and a viewpoint from another angle where we can identify all those different points and where they are. So I suggest to really take a good look at this and see how this is working out. Now, aside from finding that critical point in the beginning, what we really worked on was the boundary. and the boundary is that circle, x squared plus y squared is equal to 1. And so instead of going through the mess that we went through, because you're talking about a boundary, that's like a constraint. And so I redid this boundary problem by using Lagrange multipliers. Did I use Lagrange multipliers? No, maybe I didn't use Lagrange multipliers. Yeah, Trevor and I were talking after class, and then we talked about another point of view here. So this is another point of view. Lagrange multipliers isn't here. I did it, I think. Example. Yeah.
So, for example, on the exam, can we, if we have a function where there's an immediately obvious constraint to the domain, like z equals x squared y squared, obviously any real numbers you put in will be greater.
Positive.
Will result in something that's greater than or equal to 0.
Yeah.
So you could say then that the minimum is greater than or equal to.
Yeah.
And then if we do the second derivatives and either and one of the pure lines, so to speak, like for fxx or fyy,
Mm-hmm.
is equal to 0, then can we say, can we just stop the, if we're looking for maximums and minimums, we can just stop right there and say we can't use the second derivative test of maximums and minimums, because any value just plug in what we gave guys, or any points you find that results in either
0 or positive.
less than or equal to 0. Because if fyy is 0 for all y or for all xy,
Then it could still be 0. It's not that it wouldn't exist anymore.
No, I'm saying we can, if we find that one of those is always that, we can use it as rationale for skipping solving for critical points with that, because
I think we're going to have to take a look at an example of what you're talking about. I need something more specific because I'm not seeing the logic right now. So back on this is the same problem that we were working on. So I have another document that's a little bit extended, and in this extension you can use a Lagrange multiplier. So this could be another example that you can look at and then compare to what we did earlier with looking at the boundary and doing those substitutions to make sure that you actually get the same results. So in this particular example, we did Lagrange multipliers. I solved for x and y, and then I ended up with 1, 2, 3, 4, 5, 6 points to look at. And so those are essentially the same 6 points that we saw with taking a look at the boundary and doing the substitution. And then we plug in those, and then we get the results. And then this also has an accompanying picture of the constraint, which is a circle, and a bunch of level curves, and some of the other level curves are highlighted in different colors. And so we can see those level curves, that they're actually tangent to the constraint. Okay, so there's other level curves that look like they're intersecting the constraint, but their intersection is not a kissing intersection, so they don't have the same direction of, or they don't have the normal vectors, which are the gradients that are collinear. Okay. So anyways, I'll post this version up online in today's lecture once I get the week 11. This is a week 11 now. Once I get that, I'll post this document, and I really encourage you to take a look at it and see how this relates with what we were just talking about last week, a couple lectures ago last week. Okay? All right, let's go back to what we were talking about, Lagrange multipliers, and a quick summary. So I want to just do a couple more problems, and I just want to remind you of what the basic equation is. So we find for Lagrange multipliers, we're trying to maximize or minimize a function z is equal to f of xy subject to constraint and then the constraint, we ended up looking at it as a function of x and y equal to a constant. And then the main formula for this is we need to solve for the gradient of f of xy equal to some scalar multiple of the gradient of g, and then get the xy values that would form the solution for that. Now remember, there are lambdas that might come up there too. We don't need lambdas, we don't care about those lambdas, but if we get values for those lambdas, that's fine. But more importantly, we need to find those x and y values and then check f of xy to find the max and mins. So the general outline and idea of this is really, really simple. The difficult part is when we set this equation up, what kind of algebra do we need to use to solve for x and y? Okay? So let's see. So I want to do one more problem in 2 dimensions, and then we'll up it to 3 dimensions, and then we'll just take a look at hopefully some different types of equations to solve for, different processes. And for this, I wanted to, let's see. Start with something 2-dimensional. Five or 6? Have you guys looked at the homework? See if it's any of these. Want to pick one? 5 or 6? Six. Let's take a look at number 6. So the function that we're trying to maximize or finding extreme values for is e to the xy, and then we have a constraint of x cubed plus y cubed. All right, so the idea and the first couple steps are easy enough. We find the gradient of f, which is e to the xy times the derivative of x with respect to the derivative of xy with respect to x, which is y. And then that's the first part of your gradient, and the second part of your gradient is e to the xy times the derivative of xy with respect to y, which is x. And then your gradient for g is equal to 3x squared and 3y squared. So we're going to set them equal to each other. With a lambda. And then we're going to come up with 2 equations and 3 unknowns. So these are the 2 equations that you get from the gradient, and then you will also take your third equation, x cubed plus y cubed equal to 16. So here's your 3 equations and 3 unknowns. And so somehow, some way, you're going to need to solve for this x and y, and if need be, lambda, to try to figure out what's going on in this situation. So, any ideas? Put it into Wolfram alpha. So here's a, yeah, you don't get Wolfram alpha on the test. Yeah. For which equation? And then, yeah. (16 minus y cubed to the 1/3 power). Put that into x. Ooh. Yeah. I don't know. Oh. Yeah, I don't know. Not looking good. Just look at the time. Whenever we divide by a variable, we just want to make sure that we account for the possibility of that variable being 0, and so we want to save that. So what do you want to do? By? Oh, divided by each other? That cancels out. We have x over y equals lambdas canceled, 3's canceled, x squared over y squared, y over x. And then we have what? X cubed is equal to y cubed. Is that right? X cubed equals y cubed. And what do you want to do with that? Oh, stick into the what? The third one? Oh, cool. We got it. X cubed plus x cubed. Well, x cubed is equal to y cubed, so I'll put x cubed here is equal to 16. So 2x cubed is equal to 16. That's 8. X is equal to 2. Is it plus or minus? Yes? No? No, because it's negative. Negative times a negative times a negative is negative, and this is positive 16. So x is equal to 2. And then y is equal to 2 also. So we have that point, 2, 2. Cool. Since we divided, we have a possibility of the x being equal to 0, y being equal to 0, so we want to take that into consideration. So when x is equal to 0, what's y equal to? So we divided by x and y. That's essentially what we did here, right? The denominator had x and y. So whenever we divide by a variable, we always have to take a different case. So a case where x is not equal to 0 or y is not equal to 0, this is okay. So this is what we get. But a separate case, what if x does equal to 0? We couldn't have divided, so let's assume that x does equal to 0 and see what we get. And if x does equal to 0, we'll take a look at this first equation or the second equation. We have 0 equals 0. Let me write that out more formally. X, I'm looking at the second equation, e to the 0 times y is equal to lambda. Lambda, by the way, is non-zero. Lambda should never be equal to 0. Is equal to 3, oops, not equal to, times 3y squared. And so we would get y is also equal to 0 here, right? Is that correct? So here we have another point that we need to consider 0, 0. Do you understand this, that we have to consider this situation? Is there a problem? Yeah, 0, 0 wouldn't satisfy the constraint, right? So 0, 0 does not satisfy x cubed plus y cubed is equal to 16. So we have to cross it out because it has to satisfy all three equations. Anything else we might need to consider? Yeah? Yeah, we should, but I think the same thing is going to happen, right? Yeah. So when y equals 0, same result. And then 0, 0 is not a point. Okay, so we only have one. And so we should put that into the equation. So 2, 2, f of 2, 2 is equal to, what is it? E to the 2 times 2, e to the 4th. So it looks like if we have anything else aside from 2, 2, we have e to the 4th as a, does everybody agree that this is going to be a maximum and not a minimum? Say it again.
Correct me if I'm wrong. If we have, say 0, 0 is part of this constraint, can we intuitively say that that was part of the constraint, and comparing it with the other value here, that it would be a maximum?
Close. Because this is not part of the constraint, we really can't consider it. But we can look at another point on the constraint, like 0, comma, when x is equal to 0, y is equal to like 2 square root of 2 or whatever. Cube root, cube root of 16, whatever that is. So, so putting another value like 0, comma, cube root of 16 here would give you the same result, which is 1. And so e to the 4th would definitely be the maximum. And it looks like according to this, we have no minimum. I don't know if I believe that. Yeah, we can graph it. Oh, I don't have my graphing calculator ready. There you go. So e to the xy, z equals e raised to the x times y. Looks like this. So it looks like we might have a maximum. Positive 2 and positive 2 is somewhere over here on the positive x-axis, x and y-axis. Let's draw the constraint. The constraint was x cubed plus y cubed equals 16, and I think I might need to zoom out. Oh, yeah. So it's only on this side. And then this, I'm assuming this red graph, can you guys tell the difference between the red and green? Let me put this in blue. So this red graph over here goes on forever along the axis, and so this, and then this blue graph is just going to continue to go down to 0 and never touch it. It's like the exponential function. So it looks like that's the deal, and it looks like it doesn't have a minimum. All right. Any questions? Oh, we can actually check our answer, I think. Was it this one? E to the 4th and dne. Well, I hope it's right. Is it? Did it go? Yeah. Okay. So, yeah. Oh, so we got this. This is the point, and this is a point in the domain, and this is a value. point in the domain, not only in the domain but also in the constraint. And so Matt actually suggested something kind of good where we put 0, 0 into the function, but 0 is not part of the constraint. So if I randomly pick another point on the constraint, pick another point on the constraint, like maybe if x is equal to 0, then y is equal to, this is a little math that I was trying to do earlier, and I was trying to do some radical stuff in my head, but I couldn't figure it out. So it's just the cube root of 16, that would be if x is equal to 0 and you solve for y. And then you put that into the function, 0 comma the cube root of 16. That's e times 0 times the cube root of 16, which is going to be e to the 0, which is 1. And this is larger than 1. And so any other point that you would choose, you would assume that it's going to be less than 1. All right, so let's throw the graphics in there. In our notes. And let's see, maybe if I, transparency, okay, all right, knock it off. And maybe I'll make the z value, e to the 4th, what's that in your calculators? It's like 20 or something, right? It's not even 20. It's past 20. So anyways, I'm trying to look at the height here to see what the largest value is. Maybe if I stop it right around here, we're looking for this constraint in red, how far it goes until it reaches and intersects up here somewhere. So that's the value that we're looking at, or that we're looking for. This is a three-dimensional graph of it. But remember that this whole idea of Lagrange multipliers was based on a two-dimensional graph of it. So let's take a two-dimensional graph and see how that's going to go. So the two-dimensional graph, if you remember, we're looking for level curves. And I can't put 0 here because e to the xy is never going to equal to 0. So let me start with 1. And I don't see 1. That's probably because, yeah, I don't know how far I need to go. Maybe 5. Okay. Oh, there it goes. 4. 3. Oh, maybe 1 is just the axis. Yeah, because either x or y has to equal 0, so it's the x and y axis. So that's why I didn't see it. So if we take a look at these things, it'll at some level, this thing will eventually be touching this curve over here, right? And what I could do is I can try a bunch of different values. I have 3, 5, and 7. And so what if I want to jump to figure out what the z value is? So what do I need to put for this value for the level curve so that it's actually kissing it? We actually did this. We did the work already. And so the answer is in our answer. What? Do you understand my question? I guess you should understand my question before you can answer it. You understand my question? Say it again? E to the fourth, yeah. So that'll be our maximum value. So that's going to give us the z value, the height. And so if we change this to e to the fourth, then we're here now. We're actually looking at the curve that's going to be tangent, or whose gradient vectors are collinear. That means the graph itself looks like the two graphs are kissing. Okay. So these are different level curves for our graphs. And we found some level curves, and these are labeled as levels. I think this is 3, 5, and 7. Z is equal to 3, 5, and 7. And then this curve right here is z is equal to e to the fourth. And this here is our constraint. Okay? And you can see at that point, 2, 2 is where we hit that maximum. That point on the x-axis would be over here, and this is the point 2, 2, e to the fourth, where this red graph will eventually intersect the blue graph in 3 dimensions. Okay? So I hope these pictures are kind of putting things together for you. If not, take a good look again. Take a good look at the notes again and understand the theory and the concepts behind this thing. All right. Let's try one in 3 dimensions. Now, imagine ourselves in 3 dimensions. The function that we're looking at is some function of x, y, and z. So the output would give us a 4th dimension, which we can't picture anymore. But if we can drop ourselves down to the dimension of the domain, f of x, y, z has a domain of 3 dimensions, the x, the y, and the z. Even though there's a 4th dimension added to it, we can still take a look at the level sets, which are going to be surfaces. So that's what we're going to do. All right, so let's do an example in 3 dimensions or higher dimensions. Number 7 or 8. 8 is interesting. Oh, sorry. I wanted to do one more thing. Because I know a little trick. I mean, Caroline's idea is really great when you divide everything and then you get this nice setup. But here's another trick to doing one of these things. To get to where she got over here, I can multiply this by x, multiply the first equation by x, and I would get xy e to the xy is equal to lambda 3x cubed. And I want to multiply this by x because I want to get x cubed a little bit more involved in the other 2 equations. And then I'll multiply this by y, so this is times x, xx, times x. And this is times y. If I multiply this second equation times y, I'm going to get xy e to the xy is equal to lambda 3 times y cubed. And I'll see that those 2 things are equal and eventually come down to say x cubed is equal to y cubed, which is going to give me the same result. Okay, so this is just another way to solve. Okay? So anyways, over time, you kind of, the more you do this, the more you develop tricks. So I don't know how long you guys are going to be doing this. Maybe after this you're done. Or maybe in some of your econ classes or your physics classes or your engineering classes, you might have to do some more Lagrange multipliers in the future. But the more you do this, the more tricks you kind of accumulate. Fair? Yeah, that's another. So anyway, there's things that are equal to each other. Like you have factors of e to the xy for both of them. You can solve for that, and then find your way to set them equal to each other and get the same results. All right, back to our higher dimensional problem. So now our lambda equations. We will have 3 lambda equations and a 4th equation, which is the constraint. So we're going to solve for x, y, z, and if we need to, lambda. So that's 4 unknowns, and we're going to need to come up with 4 equations. And I just told you where the 4 equations are going to be coming from. So the gradients will look like this. So since our domain is in 3 dimensions, our gradient should be a 3-dimensional vector. So the derivative with respect to x is a variable, y, z are constant, so that's just going to be y, z, and then here it's going to be x, z, and then x, y. If you take those derivatives with respect to x, with respect to y, and with respect to z. Our constraint looks like this. So it's x squared, 2y squared, and 3z squared. So we have 2x and 4y and 6z for our second gradient. And if we set them equal to each other with a scalar multiple lambda, we're going to come up with 3 equations. The first one is yz is equal to lambda times 2x, and then we have xz is equal to lambda times 4y, and then xy is equal to lambda times 6z. So aside from this, we can say this is so far 3 equations, but we have 4 unknowns, and so our 4th equation is going to be your x squared plus 2y squared plus 3z squared is equal to 96. So now, what do we do? When we do substitution, what are we going to substitute for where?
With those relations, pull out on the right side, you can pull out the
2 lambda. But if we take it out, what are we going to do with them? We could divide by 2 lambda, I guess. So yz divided by 2 lambda is equal to x. Xz divided by 2 lambda is equal to 2y.
What I was going for is you have a 2 lambda on that side, remove everything, or divide by the stuff that isn't 2 lambda, and then you can relate the, and then you have a thing that all of them.
So if we divide by x, maybe.
Yeah.
So divided by x, we get 2 lambda is equal to yz divided by x. 2 lambda is equal to xz divided by 2y, and 2 lambda equals 3, or xy divided by 3z. And we'll set them equal to each other. Any other suggestions? Yeah, see, this is where it gets kind of crazy, yeah. Solve this one for y. Solve this one for y. So y equals lambda 6z divided by x. And what? To the second one, xz equals lambda 4 times y, which is lambda 6z over x. X squared, z's cancel. 24 lambda squared. Okay. Yeah. Good. Hey, how about that little trick I just talked about? Think about this. Feces. What are you going to do? You can't just tell me?
I was just doing divide.
Oh, that's the same thing, I think, the dividing.
Yeah, but then I could just substitute everything to the equation.
Mm-hmm. Well, I was going to do something a little different.
Yeah. Right.
Let's take a look and see if we get the same result. The idea of this little technique is to get one side to look the same so we can set them equal to each other. Right? And so if we take a look at this, we have yz, we have xz, we have xy. So there's something missing in each of them to make it look like xyz. So what if we multiply the first one times x? We have xyz is equal to 2 lambda x squared. Or let me see. Yeah, let's just say 2 lambda x squared. And the second one, if we multiply it by y, we get xyz is equal to 4 lambda times y squared. And then the last one, multiply that by z, we have xyz is equal to what? 6 lambda z squared. I guess I should have written the other two a little bit more carefully. I can rewrite this as 2 lambda times 2y squared, and I could rewrite this as 2 lambda times 3z squared. And if I write it like that, the right-hand side looks awfully close to the constraint.
Divide by 2 lambda
Yeah, so xyz divided by 2 lambda, and I can divide by lambda because lambda should never equal 0. So I got x squared is equal to xyz divided by 2 lambda. 2y squared is equal to xyz over 2 lambda, and 3z squared is equal to xyz divided by 2 lambda. So they're all equal to each other. Yeah, so we can set them equally each other and just say that x squared is equal to x squared. 2y squared is equal to this, which is equal to x squared. And 3z squared is equal to xyz over 2 lambda, which is also equal to x squared. So x is equal to, so that's 3x squared divided by, or is equal to 96. Divided by 3 is 21? Is that, no, 32. 32? And then take the square root of 32, and probably want to consider a plus and minus because it's being squared. So it looks like we have x is equal to plus and minus square root of 32, and we can solve for y squared by looking at that. So let me do this. X squared is equal to 32. So x squared is equal to 32, which means 2y squared is equal to 32. And so y is equal to 32, 18, the square root of 18. And then z is going to equal to plus and minus the square root of 32 divided by 3, I think, which doesn't seem to come out to be a nice number. So I have 2 possible choices for x, 2 possible choices for y, 2 possible choices for z. It looks like I have to take a look at all the combinations of them. Did you get the same answer, by the way, when you did it? Okay. So possible choices for x, y, and z are a combination of all these pluses and minuses. How many points do we have to check? Suppose we can list it all down. So we're going to check f of, consider when they're all positive, square root of 32, square root of 16, square root of 32 over 3, and then all the different combinations. So plus, minus. When you square them, because that's what you're going to do, it's going to come out to be positive anyways, right? Wait, you square them? It's what? Oh, yeah, sure. All right, I'll write it neater. So we put those values of combination. So it looks like the function itself is the product of just x, y, and z. So it looks like your answer is going to be positive or negative depending on the different combinations. So I think if we just multiply all this out, we're going to get whatever we're going to get. So 32 times 32 under square root is 32 squared. And then you multiply it by 4, 128. 128 over square root of 3. So if you have an odd number of negatives, then it's going to be negative. If you have an even number of negatives, it'll be positive. But those are the only possible combinations. So I think that's your maximum and your minimum. Check also all the other combinations, plus, minus, 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 etc. Okay, should we check? Let's just assume that we're right, even though we're not. Let's check. 128 over root 3. Oh, shoot. Okay. All right, any questions? Yeah. Say it again? Yeah, right here. Okay, so this is one of several tricks that you can use to try to find the solutions. Others would be just a bunch of random substitutions that you can try to do to try to get values for x, y, and z. And again, if you need to find lambda, go ahead and find it. That'll help you solve for this. And you may get more than one value. You may get only one value depending on the particular situation. Any questions? All right. So that's let's take a look at how we would kind of view this in 3 dimensions. So in 3 dimensions, what we would want to do is, this is our constraint. We would graph the constraint as if it was just a constraint. And then we would take a look at x, y, and z as a bunch of level surfaces. So this is a function that we're actually maximizing. So let's see. We have, I'll do the constraint first, x squared plus 2y squared plus 3z squared equals 96, and this looks like it's a big number, so we're probably not going to see it initially until we zoom at a particular space. Oh, thanks. So we should have known that was an ellipsoid, right? The x squared plus y squared plus z squared are all positive, and then you have different coefficients for the x, y, and z. So this is our ellipsoid. Now let's take a look at our function. And for our function, x times y times z is equal to, we want to change this to a bunch of different possible values to see how it might look like. And these level surfaces, they're changing really subtly. I should stop it from spinning. Actually, we don't need to make that transparent. This one we'll make transparent. So it's a subtle change. So let's change our n values to go to 30 with steps of 100. And then you can see how the level surfaces change over different values of n. So I have my n going from 0 to 30, and it looks like I'm not reaching. What number do I put in here again to make sure I get my level curves to just be kissing, or in this case, level surfaces? Do you remember? Sounds like it's going to be a big number, right? Because I'm 30, it's still not going out there. Yeah, 128 over root 3. So if I get that 128 over root 3, then I will be exactly tangent to the surface. Let's put this in blue. And it looks like it's tangent to the surface at a couple of different places. Right? But these are only the places where it's a maximum. So just to confuse things a little bit, graphically confuse things a little bit, the minimums happen when it's negative. Now, you can't visually see the maximums and minimums here because the maximums and minimums are in the fourth dimension, right? But you can see those places where there are a maximum and a minimum. And one of those places where it's a maximum is what? Do you remember what those values were? The x is equal to the square root of 32, the y was equal to 4, and the z was equal to, square root of 32 divided by 3. And so remember, the blue graph is where I have my maximums, and so here's one of the points. My minimums occur when at least one, or if you have an odd number of negatives. So one of those, if we make the last one negative, here's another point over here. So remember that the green graphs are the minimums, the blue graphs are where the maximums happen. And so we have this purple dot on the maximum, we have this teal, light blue dot where there's a minimum. And it's with the green graph. So I don't know if this it makes a lot of sense. I think one of the key things to remember is that the graphs themselves don't show you the maximum or minimum. It at least tells you where the maximum and minimum is. So let's take a snapshot of this and annotate it just so we can try to understand the graphics behind a Lagrange multiplier problem in 3 dimensions. So the blue graph is a level curve x, y, z is equal to 128 over square root of 3. The green graph are level curves x, y, z is equal to negative 128 over square root of 3. And the red graph is your constraint, x squared plus 2y squared plus 3z squared is equal to 96. And now we have found a point to, square root of 32, comma 4, comma square root of 32 over 3 is one of the points. There will be another one over here as long as we're tangent to the blue graph we're looking at, looks like x is still positive, square root of 32. Y is negative, negative 4, and z is negative, negative root 32 over 3. So here's another point where we've achieved the maximum. So the minimum points, let's put max here. So the minimum points happen at a sample point like this. It should happen at like 6 points or 3 points. This looks like it's going to be 32, square root of 32, 4, and negative root 32 over 2. And this is a min. And then another point where it touches the green graph would be another place where you would have a minimum. And this would be at the point, it looks like my x is still positive, 32, y is negative now. And it's above the z-axis, it's above on the positive z-axis, so the z is positive. So this is also a minimum because it gives me a negative value. So here are 4 points that we can see. There's 4 more points behind. I guess there's a total of 8 points. Is that right? 4 plus 4 is 8? So 8 points, 4 maximums and 4 minimums. And you can look at the combinations of positives and negatives to figure out which is max and which is min. And that will get you to the 8 different points where we have a maximum and minimum. Okay? Is this cool, or are you guys looking at this like, oh, shit, what did I get myself into? All right. So look over some of these documents, look over some examples. Visualization is good, and good luck.